Okay, so today we're going to look at the definition of Euler's number, also known as E. So with this, we see this number a lot everywhere, but sometimes we don't go to the definition to see what it actually means. So Euler's number is a real number, and it can be defined in two ways. And the goal of this video is to show that these two ways are equivalent. So the first way to define E is as a series, an infinite series. So we define E to be the infinite sum from k equals 0 up to infinity of 1 over k factorial. So in other words, it's 1 plus 1 over 1 plus 1 over 2 factorial, 3 factorial, and so forth. And the second way to define this is as a limit of a sequence, as the limit E defined to be the limit as n goes to infinity of 1 plus 1 on n to the power of n. So since we don't know a priori whether these two definitions are the same, I'm going to denote the second E to be E prime. And then we're going to show that E equals E prime, so that in fact these two definitions agree. So the first thing about an infinite series like this is, how do we know it's well-defined? How do we know that it doesn't just go to infinity or it's just undefined, right? Well, in this case, we're going to use the monotone convergence theorem. And this theorem states that if you have a series like this, and the whole series, the partial sums of this series are all bounded above by some positive number, and every partial sum is a non-negative number, that means this series converges. So we first have to find an upper bound for this series. Actually, it turns out in this case it's not too difficult, because we see that this is less than or equal to 1 plus 1 plus 1 half. And at the term 1 over 3 factorial, we're going to notice that 1 over 3 factorial, which is just 1 over 3 times 2, is actually less than equal to 1 over 2 times 2. So that's 1 over 2 squared. So I'm going to write plus 1 over 2 squared as the upper bound. And then 1 over 4 factorial is going to be less than or equal to 1 over 2 cubed, and 2 to the 4th, and so on. So E is less than this infinite sum, but this infinite sum can be computed because we all know that 1 plus half plus a quarter plus 1 over 8 plus 1 over 16 and so on, that adds up to 2. So this is actually equal to 3. So that means this infinite series is bounded above by 3. Okay, so that's the first part of the monotone convergence theorem. The other requirement is that it be a monotone sequence, so that every term of the series has to be positive or non-negative. And that is indeed true here, because every term here is just 1 over k factorial, which is a positive number. So therefore, we conclude by the monotone convergence theorem that E exists. So in other words, the limit, or this infinite series exists, is well defined. Great. Now we have this second definition, which we want to first make sure it's also well defined. So how do you see this? Again, we try to use the monotone convergence theorem, but this time for a sequence. So let's call each of these terms Tn. So Tn is the term 1 plus 1 on n to the power n. And we want to see that this sequence of terms is monotonically increasing. So for this, here is an algebraic trick, or an algebraic rewriting of this expression. So we're going to write Tn as the following. So we're going to expand it out using the binomial theorem. So by the binomial theorem, we have 1 plus n times 1 over n plus n choose 2 times 1 over n squared, all the way up to n choose n times 1 over n to the power n. So that's equal to Tn. Now that's equal to 1 plus 1 plus, I'm going to write n choose 2 times 1 on n squared a little bit differently. So I'm going to cancel out one of the n's and write n minus 1 over, actually maybe 1 over 2 factorial n minus 1 over n. So one of the n's cancelled out from the top and bottom. The next term is going to be 1 over 3 factorial, and you have n minus 1, n minus 2 over n squared. And the last term will be 1, because that's n choose n, times n minus 1, n minus 2, up to 1, the last term, divided by n to the power n minus 1. Okay, so what's so good about writing it in this way? So firstly, what we see is that this is very close to the expression for E. This is actually very close to the first definition of E. We have all these factorials, reciprocals. And the second thing is that we can see that it's an increasing sequence. Yeah, so the easiest way is probably to rewrite it as this: 1 plus 1 plus 1 on 2 factorial, 1 minus 1 on n, plus 1 on 3 factorial, 1 minus 1 on n, 1 minus 2 on n. The last term is n factorial 1 minus 1 on n, dot dot dot, 1 minus n minus 1 on n. So you can check that these two things are the same. Now we see that if n increases, this term in the brackets gets closer to 1, so it gets larger. So it gets larger with n. And so do each of these terms. And at the same time as n gets larger, we have more terms. So if we have more terms and each of the terms gets larger, then the whole thing gets larger. So therefore, Tn is monotonically increasing. So that's the first requirement. The second requirement of monotone convergence is that it has to be bounded above by something. Well, so this is where the comparison with E comes. Each of these brackets is strictly less than 1. But other than that, this is actually just the partial sums of E, right? So we see from this that Tn is actually less than or equal to the nth partial sum of E. So that has to be bounded above by E. So then we can use monotone convergence. So by the monotone convergence theorem, E prime exists. It's well defined. Okay. And now, finally, so we have these two well-defined numbers, E and E prime, both of which, actually we already know one relation. We know that E prime is less than or equal to E because every one of its, of the Tn's is less than or equal to E. So therefore the limit of the Tn's is also less than or equal to E. Right? So E prime is less than or equal to E. So it remains to show that, E is less than or equal to E prime. For this, we're going to use a limiting argument. So we're going to take the expression for Tn here, but we're going to cut it off at a certain point. So this expression goes up from 1 up to 1 over n factorial. But instead of n factorial, we're going to cut it off at m factorial for some m less than or equal to n. So this expression is going to look like the following. 1 plus 1 over 2 factorial, 1 minus 1 over n, plus 1 over n factorial, 1 minus 1 over n, 1 minus n minus 1 over n, right? And because this is only part of the expression for Tn, this is clearly less than or equal to Tn. And we're going to fix this m. It's not going to change. So fix our m, which we had is less than or equal to n. And we're going to take the limit as n goes to infinity of both sides. So the limit as n goes to infinity of both sides. So you're going to get the limit as n goes to infinity of Tn, right? So what's in the brackets is exactly this thing here. So what happens? As n goes to infinity, this thing goes to 0, this thing goes to 0, this thing goes to 0. So it actually just becomes 1 plus 1 plus 1 on 2 factorial times 1 plus dot 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 plus 1 on n factorial times 1. And on the right-hand side, you've got the limit as Tn goes to infinity, that's e prime by definition. So the mth partial sum of e is less than or equal to e prime. This is true for every m. For every m. And so therefore now we can take another limit in m. So now we take a limit of this expression as m goes to infinity. So of this thing. And it's less than or equal to the right-hand side, because the right-hand side is constant in m, so that's still e prime. But now the left-hand side is by definition e. So this implies that e is less than or equal to e prime. Okay, so that's the other inequality that we wanted. So if we combine this, e is less than or equal to e prime, together with this here, e prime is less than or equal to e. If I can just box that. These two things together imply that e is equal to e prime, and we're done.